Good afternoon, and thank you for coming. I'm Mark Brown, CEO of Berger & Brown Engineering, makers of SmartFlow products, offering engineered solutions through precision machining and engineering design. SmartFlow has been offering engineered products to the plastics industry for 21 years. Our product offering has grown from a lonely plastic modular manifold at our first NPE in 1991 to 14 trade names: SmartFlow, Dr. Eddy, Fast High, Speed Bar, to name a few. 10 patents, thin switch, fast high, swap valve, so on, including a broad line of mechanical and electronic flow meters, a broad line of stainless steel and aluminum manifolds, in-mold sensors, mold temperature regulators, flow regulators, ejector tie-in systems, and selectable water, air, and purge systems. So as you can see, we've grown a little bit. Today, I'm happy to announce that RJG has integrated our tracer flow meter into their data acquisition system, the eDart. This is great news for customers. This will give customers the opportunity to monitor and record temperature and flow in their cooling circuits. Again, I say this is great news. What's more is that through this collaborative effort, an even bigger need was discovered for the molding industry: the need for a training regimen for helping processors better understand cooling. Does anybody know what the typical cooling time is as a percentage of overall molding cycle? A show of hands. Is it 30%? Is it 80%? Is it 65%? Is it 50%? If you said 80%, you're correct. Knowing this, coupled with the fact that mold cooling is typically an afterthought, we at SmartFlow have decided to develop this training regimen. It's called scientific cooling. At this time, I'd like to share with you a promotional video that we created to introduce scientific cooling, as well as promote SmartFlow's product offering with regard to scientific cooling.
The principle of scientific molding seeks to optimize molding efficiency by measuring and recording molding process parameters to the greatest extent possible, providing an effective means of easily repeating a successful molding setup in any molding machine. One of the key elements of the molding process is mold cooling. In fact, experts estimate that mold cooling time represents, on average, 80% of the molding cycle. Scientific cooling, a training regimen developed by SmartFlow, applies this same principle to mold cooling, namely, measure, record, and repeat. The teaching of scientific cooling requires the right tools to measure, record, and thus quantify the cooling parameters. SmartFlow's patent-pending Delta Q flow regulators are the foundation of a flexible, modular system that can control, measure, and record cooling parameters to allow all molders to affordably apply scientific cooling. In addition, scientific cooling methods can help meet sustainability objectives by achieving effective cooling while using the minimum flow rate necessary. Over the next few minutes, we will introduce and demonstrate the new SmartFlow platform to apply scientific cooling, Delta Q. Combine Delta Q with our Ice Cube flow meter system. The venerable Ice Cube meter is our simplest, lowest cost flow measurement tool. It features an array of modular accessories to measure temperature and pressure in addition to flow. Used in conjunction with our turbulent flow reference chart, molders can easily adjust for turbulent flow. The Ice Cube meter is available with several scales in both gallons and liters per minute, and with a variety of thread connection options in both NPT and BSP. Delta Q with the Ice Cube, basic tools for scientific cooling. Combine Delta Q with Dr. Eddy for the simplest way to achieve turbulence in your cooling circuits without using excessive flow. The benefit of turbulent flow in cooling channels has been long understood by injection molders. Turbulence in a cooling circuit depends on the size of the channel and the speed and viscosity of the water. And since viscosity increases with lower temperature, you could instead say that turbulence depends on channel size, water speed, and temperature. Wouldn't it be elegant to have a meter that would take all these variables into account and simply indicate whether flow is turbulent or not? The patented technology of Dr. Eddy does exactly that using FCI technology, Fluid Characteristic Indication. Here's how FCI technology works. An FCI technology scale has 3 zones. The laminar flow zone has parallel red lines, and any flow in this area should be considered laminar. The gray area is the transitional flow zone, turbulent depending on water temperature. Turbulence is established in this area by merely adjusting the flow to the temperature marking that matches your water temperature. Finally, there is a turbulent zone with wavy green lines to indicate that any flow in this area will be turbulent. To allow for different cooling passage sizes, Dr. Eddy has selectable scales, easily positioned with a thumb wheel. 3 scales incorporate FCI technology, each for a common cooling passage size. The blue scale is simply a flow rate scale. As glycol does affect viscosity, Dr. Eddy has correction scales, depending on the percentage of glycol used in your cooling system. Just let us know in advance when ordering, so we can apply the correct FCI technology scales. Dr. Eddy truly makes checking for turbulent flow as easy as 1, 2, 3. Just select the scale that most closely matches the diameter of your cooling channel. Note the water temperature. And finally, adjust the flow to match your water temperature. It really is that simple. Combine Delta Q with Tracer for the ultimate in cooling function control and monitoring. The SmartFlow Tracer electronic flow meter, now in its 14th year of production, provides precision electronic measurement of flow and temperature. Built around a powerful microprocessor, Tracer offers a host of advanced features and functions, including battery power or remote power, easy-to-read digital display, automatic BTU calculations, selectable English or metric units, programmable alarms, analog outputs for automated process monitoring and recording, selectable corrections for glycol water solutions, and patented FCI technology to directly indicate when flow is turbulent. Tracer and Delta Q, professional tools for scientific cooling. Scientific cooling for precision and profits. SmartFlow, leading the way.
We believe by employing scientific cooling, customers can develop sustainable, a key word, sustainable solutions for the optimum cooling before the steel is cut in new molds and solve cooling problems in existing molds. With that said, I'd like to introduce our own mad scientist, the gentleman who will be running our own lab and developing the curriculum for scientific cooling, Mr. Phil Berger.
Okay, how's that sound level? Okay in the back? Well, as Mark indicated and showed with his slides, the mold cooling portion of the cycle is big, and as a result, we think that's an excellent place to look for improvement in your molding cycle. Cooling seems like a simple thing. You connect a water line here, another water line there, and you're off to the races. But really, there's a lot more to it than that. There is the thermal property of the resin, thermal properties of the mold materials, whether a part might shrink away from a wall as it's cooling and introduce an air gap between the steel and the resin. Many things come into play, so it's anything but simple. So our intent with this cooling training that we intend to do is to teach the science so that folks understand some of the engineering and scientific aspects of it, but to distill it into practical things that can be used in the molding plant. So before we get into the slides where we talk about this curriculum that we intend to develop, I want to say from the beginning that we don't claim to know everything about this. We We intend to take perhaps as long as a year to develop this curriculum. We intend to do extensive research of what's been done in the past, in other words, retrospective literature research to uncover and collect things that we can teach that other folks have already done using research that's already happened. But in addition to that, we're going to equip a lab, a molding lab, and do some of our own research to fill in gaps in the knowledge as we think it's necessary, and collect something that can be useful to molders and develop this curriculum. So the slides coming up will show some of the ideas we have so far for things we think we want to talk about. It's by no means a complete list. We expect we'll get lots of input from friends and industry experts that we have relationships with, and over the next few months distill this into something that might be useful to molders. One of the first things we think is important to teach about is a little bit about the basics of energy and heat transfer. And there are thermal properties to the resin that have to do with how readily it can conduct heat and how much the heat capacity of the resin is. So that's part of the basic science. You can calculate the heat energy, or the BTUs, if you will, in a shot based on these conditions, and you can also use those things to calculate how readily the heat can be extracted from the plastic. There are heat transfer issues. How fast can the heat come out of the resin? How fast can the heat go through the steel? How the heat gets transferred into the water, and all of these things are interesting and useful for people to know a little bit about. So we also intend to teach something about heat transfer calculations. Not that we want to overwhelm people with equations, but to understand the fundamentals of how all this works. Good. So what we think is another thing that's useful for people to think about is that the mold is actually a heat exchanger. And I'd have to say it's not a very good heat exchanger, but it is a heat exchanger. The heat goes into the mold in the form of the resin, and it's got to be extracted somehow so the part will solidify and you can take it out of the mold. So you have to think about the mold as a heat exchanger. And you can calculate the heat going in using, as I said before, the specific heat of the material and the temperature and these things. And then you can also use that to calculate, that determines how much heat you have to get out to solidify the part. So that enables you to get an idea of what sort of flow rate you might have to get a certain number of BTUs out. And that gets into the applied heat transfer. How does the heat get out of the part? Where does it go? And another factor in this is if you're doing mold heating, running the mold at an elevated temperature, that can have something to do with where the heat goes. Because if the mold's very hot, a lot of the heat goes into the room rather than into the cooling system. We think it's important to talk a little bit also about coolant delivery and coolant conditioning. Pumping capacity is very often an issue in molding plants. I'd say that's a frequent problem so you have to balance the needs of your plant against the pumping capacity that you have. Temperature control is something to discuss. Chilling water, heating water, coolant temperature considerations, coolant temperature in the environment. Is it a warm, humid environment? And if the molds are at a certain temperature, are they going to sweat? Can you maybe do just as well by having the coolant a little warmer? These kinds of things. Another thing that we've done some research on ourselves. And actually written and published an article about is antifreeze agents and their effect on heat transfer. Probably most of you are aware that when you put antifreeze in, the water gets considerably more viscous. That means it takes more pumping horsepower. It takes a lot more energy to get the fluid flowing at a rate so that you get turbulent flow. So antifreeze, maybe the guys that sell antifreeze wouldn't want to hear us say this, but we think that you might want to think twice about using antifreeze. You might want to just run the water a little warmer, and you might be better off. This also plays into sustainability issues. Anything you can do to conserve pumping capacity to figure out how to optimize your cycle with the minimum amount of water that gives you a good part and a good cycle. All of these things help you save energy, maybe prevent you from having to build on to your circulating system, add more pumping capacity and all that. So we think it's important to talk about the sustainability part. So going back to the heat energy issue and the cycle time, all of this can be used to calculate how much heat you have to get out, and has something to do with how your heat energy throughput is with the mold. Effectiveness of heat transfer in the mold, like we discussed, it's water viscosity, water flow rate. Is it turbulent? Does it need to be turbulent? The turbulence isn't always the answer for everything. Sometimes if you need to get temperatures more balanced in a mold across the steel, maybe you don't need turbulence in every situation. And as I alluded to a little earlier, ambient temperature in the molding room can be a factor as well. Another thing that we think is worth talking about is design considerations for cooling circuits. There's the size of the circuit, which has to do with how much water you can pump through, which has to do with how many BTUs you can get through there. But working against that is the bigger the circuit, the more water you have to put through, the more flow it takes to be turbulent. So there's a balance there. Making the circuits as efficient as possible in terms of pressure drop, that's an important thing. Comes back to pumping capacity, pumping horsepower. Location of cooling lines to try to keep the thermal gradient in the mold to a minimum so that you don't induce warpage or have hot spots, cold spots, that sort of thing. Those are all things to talk about. Techniques for getting cooling into tight spots, bubblers, baffles, heat pipes, and that sort of thing. And then, of course, the materials that you use in mold construction can have a lot to do with the heat transfer and thermal characteristics as well. The stainless steels being the worst for heat transfer, down to beryllium, copper, and aluminum, which transfer the heat very, very quickly and readily. We also think it's worthwhile to talk about what we mean by scientific cooling and how that applies to all of this science. Mapping and recording your cooling hookups we think is important, because some people, because of pumping capacity, might want to loop circuits. And we're not going to say that that's a terrible thing to do, because it can help on the pumping capacity side. But if you have too much temperature increase in a circuit and then you loop it into another circuit, then you can be creating problems with thermal gradients in the mold. We think it's important to optimize the coolant flow to get a good cycle and a good part, and then no more flow than that. It comes back to sustainability and conserving pumping capacity. So we talk about that as a minimum good part flow rate. And again, that might not always be turbulent. You might have a situation where you can mold a perfectly good part with a lower flow rate than you expect. So not always turbulent. We also think it's very important to measure and record coolant supply conditions and incorporate this into setup sheets. There are tools, simple mechanical tools as well as electronic tools for doing this. And if you want to come back every time and get your mold set up and have that go quickly, recording all of these things and being able to repeat those, we think is an important thing to teach. Electronic sensing and this collaboration with RJG and EDART kind of plays into this. It's easy to collect data and to keep your process on track with automation that is afforded by the electronic sensing and data acquisition. And the smart sensors also have built in within them, the electronic flow meters that we make have programmable alarms that can trigger an alarm or shut something off, shut a press off if you wanted to go that far, or maybe keep you from starting a press if somebody forgot to turn a cooling circuit back on. Some of the advanced methods that we intend to get into with the development of this curriculum and the teaching is mold simulation software, which can predict the performance of mold cooling systems, maybe allow you to tweak things in the design before you start cutting steel. And also, these things are very useful for troubleshooting existing molds and maybe letting you think about how you might reconfigure things in your cooling, or a place where you might need to slow the cooling down to bring a temperature up or the like. So mold simulation, we think, is a valuable tool. We also intend to have available to us and do some research with thermal imaging and the ability to map steel temperatures as well as part temperatures. These things can help with part warpage problems, dimensional control problems, and these are things we intend to learn more about and incorporate into this this training regimen. Now, and the sexiest of all the things here is cooling circuit maintenance, like not getting scale in there and controlling water chemistry so that you don't do damage by having pH out of whack and that sort of thing. Rust in the cooling circuits. Scale and rust, I'm sure all of you know, is the enemy of heat transfer. So these maintenance things, while decidedly unsexy, they're really, really important. So we want to teach something about PM on a regular basis, either with chemical or mechanical descaling, making sure you put things back together the same way they came apart so that you don't end up with a baffle that's turned the wrong way or something like that. These are boring things maybe, but they're really important in making sure you keep your tool working at optimum performance. I think that's a wrap. I'm going to give it back to Mr. Brown.
As you can see from Phil's presentation, Scientific Cooling's foundation will be science, simulation, and common sense. To advance the science, we intend to put our own lab together and initially, through research, prove the concepts of scientific cooling, but ultimately to use it as a classroom to teach industry professionals. I'm pleased to recognize a list of sponsors who have donated equipment and or services to our molding lab. The molding machine and the temperature control unit, as you can see, are still to be determined. We are in negotiations, and hopefully by the end of this show we'll have those two positions filled. The data acquisition system, of course, will be RJG's eDart. Thermal imaging will be a portable digital camera, infrared camera, I apologize, with digital output by FLIR. Simulation software will be a licensed seat of SigmaSoft by Sigma Plastic Services. Cooling research will be SmartFlow, care of Berger & Brown Engineering. The classroom training will be, again, SmartFlow, care of Berger & Brown Engineering in Grandview, Missouri. And then after RJG has become certified on the curriculum, they'll have the opportunity to teach this course in Traverse City, Michigan. The ancillaries, flow meters, regulators, manifolds, etc., will be again by SmartFlow, care of Berger & Brown Engineering. As you can see, we believe that we're partnering with the top individuals or disciplines of each discipline in injection molding.